Level 1. The student. You're 13 years old, and your teacher writes a proof on the board for the first time. The claim is that there are infinitely many prime numbers. Assume the number of primes is finite, multiply them all together, and add one. The resulting number is either prime itself or divisible by a prime not on your original list. Either way, your list was incomplete. Contradiction. Therefore, primes cannot be finite. No calculator, no data, just logic, arranged carefully enough to close every exit. This is the first time mathematics feels like something other than arithmetic. Arithmetic was about answers. This is about inevitability. You start asking questions that slow the class down. Why does the quadratic formula work? Not just how to use it. Why does a negative times a negative produce a positive? Your teacher gives answers that satisfy your classmates and don't quite satisfy you. You write them down and keep the dissatisfaction. Trigonometry arrives, and you discover that sine and cosine describe not just triangles, but waves, rotations, anything that repeats. Pi appears not just in the circumference formula, but everywhere, in probability, in infinite series, in places that seem to have nothing to do with circles. You start to suspect that mathematics is more connected than it looks from the outside. You're right, but you don't know how right yet. Level 2. The undergraduate. You arrive at university, and the identity you built around being good at math dissolves in 2 weeks. Everyone here is good at math. Some of them are frighteningly good. Real analysis is the first serious confrontation. You have been using limits since secondary school. Now, you are asked to prove that they work. The epsilon-delta definition requires constructing an argument that holds for every possible tolerance you demand on the output, and finding a response you can guarantee on the input. The first time you write a clean epsilon-delta proof, you feel like you've learned to walk again, slowly, in a body you thought you already knew how to use. Abstract algebra removes every familiar landmark. A group is a set with a binary operation satisfying 4 axioms. No numbers necessarily, no geometry necessarily, just structure, defined entirely by its properties. You prove theorems that apply simultaneously to the integers under addition, the symmetries of a hexagon, and dozens of other objects at once. The abstraction is disorienting and then, slowly, clarifying. The crisis arrives in the second year, a problem that defeats you entirely, not a step you're stuck on. The beginning itself, 6 hours of effort producing nothing. You go to office hours. The lecturer doesn't give you the answer. They ask what you tried and why it didn't work. You explain. Mid-explanation, you see it. You leave with a direction and no answer. This is, you will later understand, excellent teaching. You stop asking what the answer is. You start asking why the answer has to be what it is. Level 3. The graduate student. You choose a specialization by following the thread of your curiosity until it leads somewhere narrow enough to enter. Perhaps it's analytic number theory. The Riemann zeta function, a function of a complex variable, encodes information about the distribution of primes in its zeros. Where exactly those zeros are located is the content of the Riemann hypothesis, unproved since 1859. You are not going to prove it. But you might establish a result in the surrounding territory, a small clarification of a question that has defeated serious mathematicians for over a century. Or perhaps algebraic topology, where you study properties of spaces that survive continuous deformation. A coffee cup and a donut are topologically identical. Homology groups measure holes in higher dimensions. The machinery takes a full year to build before you can use it. Either way, the dissertation requires you to find a gap in the existing literature and close it. The gap might be small. You spend months becoming the world's leading expert on a question most mathematicians have never heard of. This specificity is not a limitation. It is what depth requires. The first original result arrives quietly. A lemma, a small proof that something holds under conditions you identified. It wasn't in the literature before you wrote it. Now it is. You have extended, by a very small amount, the total of what is known. The feeling doesn't loudly announce itself. It settles. Level 4. The early academic. You enter the profession and discover that mathematical ability is necessary, but not sufficient for a mathematical career. You submit a paper you spent 18 months on. The referee report arrives 3 months later. There is a gap on page 11. The gap is real. You know this immediately. You spend 2 weeks filling it, resubmit, and the paper is accepted. This process, uncomfortable as it is how mathematics maintains its standard of certainty. A gap in a proof is not a failure, it's information. Teaching begins alongside research. You prepare an explanation of the epsilon-delta definition for undergraduates. A student asks why epsilon has to come before delta, why the definition isn't symmetric. You begin answering and realize mid-sentence your answer is incomplete. The asymmetry is the entire point. Epsilon is the tolerance demanded on the output. Delta is the response guaranteed on the input. You knew this. You didn't know you knew it until the question forced it to the surface. Every course you teach reveals something you had allowed to remain slightly fuzzy. Teaching makes you a better mathematician. This is not what you expected. The pace of progress recalibrates your expectations permanently. A year of work might produce one publishable result. A career might produce a few dozen papers. You adjust. The only criteria that last are whether the work is true and whether it is interesting. Level 5. The established mathematician. You have a body of work, results that other mathematicians cite, techniques that turned out to be applicable beyond the problems you developed them for. You proved a theorem about dynamical systems, and 5 years later a physicist cites it in a paper about quantum chaos. You didn't plan this. The result had implications you didn't see, and other people found them. The unsolved problems feel different now. The Riemann hypothesis, twin primes, the Birch and Swinnerton-Dyer conjecture. These have not yielded to generations of serious effort. You no longer believe they are waiting for someone smart enough. Some may require mathematical ideas that don't yet exist, frameworks not yet built, languages not yet invented. You understand your work historically now. The Langlands program, connecting number theory and representation theory through deep conjectures, was proposed in a letter in 1967. Mathematicians today are still working on it. Your results are part of a conversation like this, written for readers you will never meet, building on foundations laid by people you know only through their papers. The beauty hasn't faded. Understanding a mathematical structure more deeply makes it more beautiful, not less. You are still surprised by this. You expect to remain surprised. Level 6. The visionary. At this level, you are not solving problems within an established framework. You are questioning whether the framework itself is adequate. Grothendieck did this to algebraic geometry. The field had good tools. He decided they weren't fundamental enough and rebuilt the foundations using schemes, sheaves, and topos theory, a new language for understanding how local structure assembles into global structure. He didn't solve the famous problems of his era. He built the room in which later mathematicians would solve them. Andrew Wiles proved Fermat's last theorem using machinery Grothendieck constructed decades earlier for entirely different purposes. At this level, the work requires inventing mathematical objects before you can state the theorems you want to prove about them. The isolation is particular. You are working where almost no one can follow closely enough to tell you whether you're moving toward something real. The ordinary feedback of academic life is unavailable. You trust your own judgment more than is comfortable and proceed anyway. What drives this is not ambition. Ambition wants recognition. What drives work at this level is closer to compulsion. The structure is partially visible, and the question of what it actually is will not leave you alone. Mathematics is an infinite structure, partially mapped, each generation extending the map a little further into territory that remains, no matter how much is charted, inexhaustible. The visionary doesn't complete the map. They push further than anyone expected and leave behind a clearer picture of how much further there still is to go. Somewhere right now, a 13-year-old is reading Euclid's proof for the third time. Something is locking into place. They don't have words for it yet. Some of them will spend the rest of their lives building a language adequate to what they're seeing. That's what mathematics is. And it never finishes.